This evening's event is entitled Smart Fabrics, Nano-technology and Textiles, and we are very, very, very honored to have with us two esteemed guests on the panel. Associate Professor Juan Hinestroza joins us from Cornell University, where he directs the Textiles Nanotechnology Lab at the College of Human Ecology. He is a tenured associate professor in the Department of Fiber Science and Apparel Design, and his pioneering work explores new pathways for creating multifunctional fibers via the manipulation of nanoscale phenomena. Also on our panel today, we are very, very honored and delighted to have Nicole van der Elst-Desai. With 20 years experience working in the textile and apparel industry, Nicole is a valued expert in the field of textile technology, innovation, and sustainability. She is the founder of VDE Consultancy, which provides project and business management services to clients in the textile and apparel industry. Thank you so much for joining us this evening, Nicole.
Thank you.
So, without further ado, let's begin diving straight in.
So I come from Cornell University, a very small school in the state of New York. And I work in the interface between nanomaterials and textiles. And I'm going to tell you stories about how we use chemistry to modify the properties of materials so they can perform functions that they usually don't do. I have great interest in this interface between industrial revolutions that happens every 50 years. And the first one was the textile industry, and the latest one has to deal with nanomaterials, about 200 years apart. Two different dimensions. So we're talking about things that you can see, with things you cannot see, things that you can produce in large numbers, with things that you can produce with incredible molecular precision at the nanometer scale. So how many of you guys know what a nanometer is? Okay, I'm a professor, so you can ask questions, okay? That's my job. So if you think about 6-year-old kids, about 1 meter, you divide by 10, it's about the width of your palm, 10 centimeters. Divide by 10 is the width of your pinky finger. Divide by 10 is maybe a freckle. Divide by 10 is the width of your hair, a single hair. Divide by 10 is a blood cell. Divide by 10 is a bacteria. Divide by 10 is a virus. And then you divide by 10 again, and that's my domain. So you divide 9 times by 10. It's a very, very small domain. And it's very unique because materials at that domain behave completely different. So we can make gold to be conductive. We can make gold to be green, blue, yellow, or whatever color you want. Still it's the same molecule of gold. And my inspiration are these individuals here. And I was fascinated by looking at this image because the concept of a superhero, the power came from the clothing. Yeah? So you have clothing that can stop bullets, clothing that can stop the fire, clothing that can make you run really fast, low friction. And what is fascinating to me is that in 1939, none of these materials existed. Zero, none of them. But that did not prevent the designer, the people who imagined these superheroes, to think that someday they could exist. 40 years later, thanks to chemistry, all of these materials do exist, all of them. And that for me is fascinating because it's design, can design, in this case, can inspire science. And what I want to do is the opposite. I want to complete the loop on how to make my science inspire design. And that is very, very difficult because designers usually seldom talk to scientists, and scientists seldom talk to designers. They are seen like separate worlds. So the first project that we were challenged by the military was to create materials that can protect you against chemical warfare agents. So we made materials very, very thin, about 20 nanometers in thickness, one single molecule thick. Yeah? So you can put thousands of these single layers in one single fiber and you still don't notice the difference. But you can prevent how the gases go through, how the liquid goes through, how you get wet, how your humidity is managed using the same material. And then we also decided to move to create layers that were even 10 times smaller. So in this case, 10 angstroms. Angstrom is 10 times smaller than nanometer. And we created these layers of aluminum oxide on cotton, and we found that these layers can produce the same thermal equivalent of a 2-inch jacket. We can also place the particles on top of the cotton. We can control the spacing between particles, and when you do that at that scale, something very interesting happens. The space between the particles is smaller than the wavelength of light, so when the light hits, it doesn't come back in the same frequency. It can come back in a different frequency, which means a different color. So I can make any color just by changing the particles size and the space between particles. And one of our students decided to make dresses in which all the colors are made with particles, no dyes, no pigments. This is gold, silver, ruthenium, palladium. So you can make all the colors with only particles. Then we can use the same particles to kill bacteria in a very efficient manner. And we can even place smaller particles on top of the smaller particles. And then allow us to make materials that will never get wet by oil or by water. So these are materials that will never get dirty, that will never smell because the bacteria gets killed. Most of these applications are military. Imagine how many bathrooms are in the jungle. How many showers are in Afghanistan? You have to have your underwear for 3 months, 4 months, without changing. So you have to develop materials that can function and operate under those conditions. We can also place the particles close to each other and make them conductive. Then we can use the same cotton to make transistors. So basically we can make a computer from cotton. Instead of a silicon wafer, we made it from cotton. So imagine how many intersections are between fibers are in your clothing, So in a single chair like this, maybe 300,000, 400,000. So if each one of them is a transistor, you can make enough computing power on your clothing. And then we can take the same molecule and tweak it around and create color, create red, green, and blue. And this is just a piece of cotton. So I just illuminate it with different lights, and then I can create RGB. So that's all what I need to make a monitor, So now I have not only the processing based on cotton, but also a display that I can make based on cotton. So we started looking how to use these materials and how to apply them in sports. So we started working with some of my favorite sports. We're talking with tennis balls that can change color based on friction. So based on the speed of the ball, you can see the different colors. The sweat that comes from you, we can capture the sweat and understand if there is issues with low electrolyte pressure inside the tennis balls. This is with my favorite team, the Barcelona, when you have materials that change color when they are mechanically deformed, or there is a pressure-induced moment when some object hits the material. And this is the idea that I didn't like very much, because I can make all the 4 different jerseys in one single one, and they didn't like that idea because they wanted to sell 4 instead of selling 1. But I understand that, but for me it's a good challenge. So what we do is we try to keep pushing these limits to understand how to make cotton to do everything that the other fibers can make, and even better. And how we can make fibers that can respond, that can change color, that can conduct electricity, that can make calculations, that can store information, that can adapt to temperature, for example, adapt to humidity. And all that is possible by manipulation of materials at a very, very small scale. Thank you.
The last time you visited us here at the Cocoon Space, you mentioned that metallic organic frameworks can be used to create fabric that keeps you very warm in a very, very cold environment. Can the opposite happen, and how?
The same principles of heating, you need to reverse the flow of the energy. So you can do that using, for example, phase change materials that can absorb the heat from your body and transfer that to the outside. And then when you go back into the air conditioning, the cycle reverses. So these are where these materials have been studied for a long time, but they can be optimized to trigger at different temperatures. Because in the same room, at least 40% of the people will not feel comfortable, even though the temperature says that you should feel comfortable. So what is the purpose of cooling down the entire room or the entire MRT station if you can actually provide a cooling to the individual person that has the individual metabolism? Yeah.
And actually, Nicole, we were talking about this just before, and you were talking about communities that have naturally cooling technologies in the physical aspects of their clothing.
Yeah, and also one of the things that we were discussing was in Africa, you've got all those tribes are actually head to toe completely dressed in black. And for one of my customers, I was actually investigating, saying, so how does that work? So the black, why would you wear black? That would absorb heat. But at the same time, it would actually also absorb the heat from your body. So looking at that, it was actually a really interesting thing to discover that black works both ways. But like Professor said, the phase change materials are out there, and they can actually do a lot of the things that they were discussing.
If I may, I think that one thing that was very fascinating when Juan visited us here at TaFF last time was the idea that you can get consistent color and that you can get really any color from a scientific process. Because as anybody out there knows who has dealt with fabrics, you order something in 50 meter bolt, and then the next time it comes, it's a different pink. And the consistency of that, I think, was fascinating for TaFF as an association because it means that designers can then have consistency in their clothing. They can dream up a color that doesn't currently exist. What is also very fascinating for us, the way it's done. Now, Nicole, I'm going to go over to you, and we're going to talk about the dye process, which we know that the fashion industry right now, especially spurred on by fast fashion, is the second largest polluter in the world, particularly with regard to water resources. So can you maybe talk us through a bit about the ill effects of dye and how it's being remedied?
In the industry, the reason why we have such a challenge with water is not only because of the dye. I think there are multiple facets to sustainability in our industry that on color, we could actually talk from the moment that you start developing the color. Right now, DHL is doing a lot of lab dipping back and forth. I think with this new technology, you could actually eliminate that because color lives in a certain place in the color sphere. So once you know where that color sits as a designer, if you have that color in mind, you don't have to do all the lab dipping back and forth. The textile manufacturers don't have to do their lab process that they then need to replicate in bulk. So there's a lot of waste saving, both from an energy, water, chemical point of view that you would already eliminate, which is, fantastic. You will get your color straight away. The other thing is that we're all aware of all the water that's being used in the coloration of our fabrics. I was very lucky to work with one of my customers on CO2 dye, which is already eliminating water. But what got me really excited here is that none of that is needed. There is not even dyes and chemicals needed, because certain colors you can only achieve by using not very fantastic chemicals. And there are laws out there, especially Europe is very good at it. Asia, China has started to adopt some of those processes. But certain colors you can't make without certain elements that are not great for the environment or for the human being. So passing by all of that is just super fantastic. It's something that I think any of the larger brands that we kind of all know who they are, they would start trying this already in the innovation center to see what colors they can achieve and how they can actually use that.
Yeah, definitely. And I think that a lot of big brands are becoming a lot more conscientious and aware that the consumer wants sustainability, is looking for an eco-friendly solution. And I think Juan also mentioned last time, because we were talking about microfibers, and at a nano scale level, you can increase the density of fabric so it becomes an effective filter. Was that the discussion?
The issue of microfiber is a very complicated issue. So nobody wants to drink microfibers, even though we do it all the time. And so that needs to change, because the massive consumption of textile fibers are basically making everything a microfiber forest. And we don't see it right now, but if we continue this trend, we will physically see it. in our single ecosystem. There are solutions to that. You just have to find unleash the power of chemistry and material sciences to make those things happen. And then the designers to take these new technologies and make them into something appealing, because no matter how good the technology is, if it doesn't look good, people will not use it. Yeah? So in that sense, designers also have the responsibility.
At this point in time, we would love to open the floor up to questions. If anybody has any questions, just raise up your hand and we'll pass the mic around.
My question is around the nanoparticles, Professor, that you and your students are exploring. Do you also propose the application process to the fiber? And in that regard, like with things like nano-silver washes, like polygen, are they safe for the environment and for the body? Because washes always have a wash life cycle, right? So, yeah.
So we don't work with silver anymore, though. We used to work at the beginning, and so we help the government to understand what happens to the silver in the process. But there are some companies that use different methodology, use particles and physical methodologies to attach them to textiles. Those particles will detach from the clothing once you wash them. And they end up in rivers or in trees or in fish. So you will eat them. Our methods are chemical methods that guarantee a permanently attached to the material so they will not leach. But it's a very important question because some of these materials are very small, they can go into your skin. I cannot say as a scientist we're 100% safe, but what I have seen so far is that the particles are so unstable when they are by themselves that they agglomerate, they get to each other and eventually create a cluster that is big enough for the body to recognize and reject that.
We have been talking about a lot of ideology, about what can happen, about crazy ideas, and I think Nick also mentioned how fast can we see this in the near future. I don't seem to get a concrete answer or at least have something that I have a vision about. So I want to ask you more straightforward. Today I want to embark on this journey. How am I going to do it? What's the cost?
It all depends on what your application is. I can tell you right away if you are thinking on selling t-shirts or blue jeans, you are competing with price and value. But if you want to add, for example, apply medicine through bed sheets or high-end or hotels that we are working on that can guarantee that some customers cannot get infections. Then those are very specific questions, and then we can work out in our university, but also in Hong Kong, also here in Singapore. There are many other universities that can solve that problem. And then you as a business person can decide, okay, this will cost me $100,000 to test if it works, but I can sell them for 3 or 4 times the price or not. Then I will not make an effort. But it's not a single recipe for deciding yes or no. But every single dream started with a cartoon and a design. Yeah, Superman was born in 1938. Batman. These ideas that you can stop a bullet with a fiber. Imagine somebody in 1938 asking that question. You are just talking about stopping a bullet with a fiber. That's not ever going to happen. But it was possible, yeah? So you have to challenge and push the science to make that happen. And I think this is a wonderful place to make those things happen.
And I think that ultimately what is very hopeful, and with that kind of realistic question, what is very hopeful is that change can happen much quicker than we assume when people start talking, which is why we have this conversation here, which is why we are having these conversations to spark talks among a young design base with international leaders who are looking toward a brighter future. So with that, let's join me in thanking our wonderful guests, Juan Hinestroza, Nicole van der Elst-Desai. And thank you finally to our supporting partners, NUS and Tencel. And thank you to all of you for coming. We'll see you next time at the next TaFF Talks.